Okay, let's unpack this. If you spend, like, any time at all in the 3D printing world, you hit this basic material question almost right away. You start with PLA, right?
Yeah.
Super easy, looks great for models, but leave it on hot car, melts, drop it, probably shatters.
Exactly. And then you think, okay, I need something functional, something tough. So you look at ABS, and yeah, ABS is strong, durable, but wow, it can be a headache. Warping, that smell, needing an enclosure maybe. It really feels like you're forced to choose easy printing or strong parts.
Right, it's like you have to pick a side. But our sources really point to this third way, something that's honestly become a go-to for so many functional prints now. PETG, polyethylene terephthalate glycol. Bit of a mouthful.
Yeah, it is. But PETG is kind of the versatile champion here. It really does sit nicely in the middle. You get toughness, good temperature resistance, the durability you need for real parts, but it prints almost as easily as PLA. Almost.
And that mix is why it's everywhere now. So our mission today is to really dig into how PETG pulls off this balancing act. We need to get into the chemistry behind it, how it actually performs, and maybe most importantly, the pitfalls, the traps you need to watch out for before you start using it.
Sounds good.
So when you hear PETG, it sounds, I don't know, industrial. But the base material, PET, it's everywhere, plastic bottles, right? Stuff we use every single day. Which makes you wonder, why can't we just, chop up some water bottles and print with those?
Yeah, it seems logical, but pure PT just doesn't work well for FDM, for the kind of printing most of us do. The chemistry gets in the way. See, PT on its own has this semi-crystalline structure. When it cools down from being melted, the long polymer chains line up really neatly. Too neatly, actually.
Okay, neat sounds good, but you're saying it causes issues.
Big issues for printing. That super-ordered structure makes it brittle, so it cracks easily. It also makes it opaque. And maybe the biggest thing, it needs a really high temperature to melt properly, which is tricky for standard printers.
Ah, okay, so we need to stop it from getting too orderly, too crystalline, and that's where the G comes in, the modification.
That's exactly it. The G stands for glycol-modified. To make PEEP into PETG, they deliberately mess up that crystallization. During the polymerization process, they swap out some of the regular building blocks for a bigger, bulkier molecule. Usually it's something called CHDM, cyclohexanemethanol.
Okay, CHDM. Don't need to remember the name, I guess, but the effect is the key thing.
That's the real aha moment for PETG. These bigger CHDM molecules are like awkward spacers. They physically block the polymer chains from packing together so tightly. So instead of that neat, brittle, semi-crystalline structure, you end up with something that's amorphous, non-crystalline. Random.
So adding that G isn't just a tweak, it's the whole reason PETG works for us.
Absolutely. It's a clever compromise. You sacrifice maybe a tiny bit of ultimate stiffness that pure PET might have had, but you gain three huge advantages for printing. One, better clarity. That's why you see transparent PETG. Two, a lower melting point, much easier to extrude. And three, way less brittleness, much more toughness.
Right. Okay, so let's talk performance. Here's where it gets really interesting, right? Moving from chemistry to actual parts, you hear people say, oh, PETG is stronger than PLA, but then you look at the specs, the data sheets, and PLA often has a slightly higher number for tensile strength, like 50-60 MPa versus maybe 40-50 for PETG.
Hold on, yeah, let's quickly break down MPK megapascals. That's basically just the measure of how much force or pressure you can put on something before it snaps, right? It's the ultimate strength limit.
Exactly. So if PLA technically handles a bit more force before breaking, why do we still reach for PT when we need something strong for a functional part? What gives?
Yeah, it seems counterintuitive, but it comes down to strength versus toughness. They aren't quite the same thing. PLA is stiff, yes, but it's brittle. It holds that force right up until its limit, and then bang, it fails completely, shatters. It doesn't handle impacts well. PETG, on the other hand, is more ductile. It might break at a slightly lower peak force, sure, but it's much more resistant to impact. It tends to bend or deform first, absorb the energy.
Oh, okay. So it gives rather than snaps.
Exactly.
Yeah.
Which is what you usually want for things like, I don't know, brackets, drone frames, parts that might get knocked around. You want them to absorb shock, not just shatter.
And the other huge factor, unlike PLA, it won't just droop if it gets a bit warm. That thermal difference is massive in the real world.
Oh, absolutely. It's a game changer. We look at the heat deflection temperature, the HDT. That's the point where the material starts to deform under load when heated. Standard PLA gets soft around, 55, maybe 60 degrees Celsius.
Yeah, not very high. Car dashboard temperature on a sunny day.
Right. But PETG,
Yeah.
it holds its shape up to maybe 70, even 80 degrees C.
That's a significant jump. That 15–20 degree difference means your part might actually survive outside in the summer.
Definitely. Think car parts, outdoor sensor housings. PLA is usually a non-starter. PETG is often perfectly fine. Plus, speaking of outdoors, PETG actually has decent UV resistance. It holds up better than standard ABS in sunlight, keeps its color and strength longer.
So good for outdoor stuff, though maybe not permanent, heavy-duty exposure.
Right. For really long-term, constant sun, something like ASA is probably better. But for general outdoor accessories, PETG is a great balance of printability and durability. Much easier than ASA sometimes.
Okay, and what about chemicals? We see PETG used for containers, maybe jigs that contact oils or something?
Yeah, it holds up well against water, weak acids, oils, that sort of thing.
Yeah.
Which leads us to the food contact question. It comes up a lot.
It does,
Yeah.
because PTT itself is used for food containers. So PETG prints for food.
You have to be really careful here. The raw PETG plastic itself might be FDA compliant, yes. But the 3D printing process changes everything. Those layer lines, even if they look solid, create tiny gaps and pores, microscopic crevices.
Ah, places for bacteria to hide.
Exactly. And normal washing just won't get them clean. It's a breeding ground.
And there's another issue too, right? The nozzle.
Yes. Most printers use brass nozzles. Brass contains lead. And there's a risk that lead could leach from the nozzle into the plastic and then into your food or drink.
Oof. Okay, so definitely not safe out of the box.
Not for direct, continuous contact. Our sources are clear. If you really need a food-safe PETG print, you need to print it with a stainless steel nozzle, no lead risk there, and you need to coat the entire finished print with a certified food-safe epoxy or sealant. That seals up all the pores.
That's quite a process. Good to know the specifics, though.
Good talk.
Okay, let's shift gears to actually printing this stuff. The upsides are pretty compelling, right? Why it's become such a workhorse.
Oh, the whims are significant. Layer adhesion is usually fantastic. Prints come out really strong, often watertight right off the printer because the layers bond so well.
That's huge for functional parts.
Definitely. And the other massive advantage, very low shrinkage and warping. Compared to ABS, it's night and day. You can print large PETG parts reliably on an open printer, no enclosure needed most of the time. That makes it so much more accessible.
Plus, you get that nice glossy finish, and it's recyclable #1 PET, same as the bottles.
All big plus points. But no material is perfect. PETG has its own set of, let's call them quirks or traps you need to learn to handle. This raises an important question. What are the common headaches that catch people out when they first try PETG after PLA?
Oh, I know the first one. Everyone knows the first one. Stringing. The little plastic cobwebs everywhere. I swear, my first few PETG prints looked like they'd been attacked by tiny plastic spiders. It was messy.
Huh? Perfect description. Cobwebbing. PETG gets kind of gooey and loves to stick to the nozzle, so it drags these thin strands across gaps in the print. The fix is mostly in your slicer settings, dialing in your retraction, making the printer pull the filament back sharply before travel moves. Maybe dropping the temperature a tiny bit.
And if that doesn't completely fix it...
Quick blasts with a heat gun usually cleans them right up. They just shrivel away. It's oddly satisfying.
Okay, what's trap #2?
Moisture. Hygroscopicity. PETG loves to absorb water right out of the air, especially if it's humid.
And that causes problems during printing?
Big time. You'll hear popping or crackling sounds from the nozzle as the water instantly turns to steam. It messes up the extrusion, weakens the print, ruins the surface finish.
So if you hear popping, your filament is wet.
Pretty much. You need to dry it out before printing, usually in a filament dryer or a modified food dehydrator. Keep it stored airtight with desiccant too. Also, related to its gooey nature, sometimes PETG struggles with really fine details, sharp corners, or long bridges compared to PLA. It just doesn't hold its shape quite as crisply when molten.
Okay, manageable. But the next one, this one actually scares me a bit. Damaging your printer bed. It sticks too well.
Terrifyingly well sometimes, especially to smooth PEI build surfaces, which are really popular. We've all seen the pictures online. Someone tries to pry off a PEG print and rips a chunk right out of their expensive flexible steel sheet. The adhesion can be insane.
Yeah, you don't want that. So how do you prevent it? You can't just hope for the best.
No, definitely not. Prevention is key. A common tip from our sources is actually not to clean the bed with isopropyl alcohol right before printing PETG. For some reason, that can make it stick even harder.
Really? That's counterintuitive.
It is. Using simple window cleaner is often suggested instead. Or, the most reliable method, use a barrier. A thin layer of glue stick, or maybe a specialized bed adhesive, acts as a release agent. It lets the print stick while printing, but pop off much more easily once it cools. Saves your build plate.
Okay, good tip. And last pitfall, finishing the print once it's off the bed.
Yeah, post-processing is a bit more work than PLA. Sanding PETG can be gummy. It doesn't sand to a fine powder as easily. And the big one, you can't smooth it with acetone like you can with ABS. Acetone doesn't really affect PETG, so you can't get that super smooth, glossy finish chemically. You're mostly stuck with sanding or painting if you want to hide layer lines.
Okay, so let's wrap this up. What does this all mean? We started comparing easy PLA and tough ABS. PETG lands squarely in between. Needs a bit more care than PLA. Sure, you got nail retraction, keep it dry, but the payoff is huge. You get that toughness, impact resistance, heat resistance that PLA just can't touch. It really feels like the go-to for, I don't know, maybe 90% of functional parts people print.
I think that's a fair assessment. It's the ultimate utility player. Its success comes right back to that clever chemistry we talked about. That glycol modification wasn't about making the strongest possible plastic or the easiest possible plastic to print. It was about finding the sweet spot, sacrificing a little theoretical maximum stiffness from pure PE to gain massive improvements in printability and toughness. It's defined by that balance.
A strategic compromise makes it better overall.
Exactly. And maybe the final thought to leave you with is just that. How often, in design or engineering or honestly anything complex, how often is the best solution not the one that pushes a single variable to the absolute extreme? Maybe it's not about maximum strength or maximum speed or maximum of anything. Maybe the most successful designs like PETG are the ones that achieve the most thoughtful balance between competing needs, sacrificing a bit of one thing to gain reliability or usability in another. That idea of intelligent compromise, that's a lesson that goes way beyond just 3D printing filament.